So we're looking at this word that we need to get used to using and knowing what it means. Verification. I'm not giving you the title, so this is it. How do you determine if the mean is, yeah.
So it's about mean then.
All right. It's not about the mean.
Okay, then,
That's not what we're studying.
Put
We are looking at a verification tool. How do you verify if specifically the mean is a reliable measure? Okay. What is the mean a measure of?
central tendency.
Good. So we've got a measure of central tendency. How would a mean be considered a good measure? What would you expect it to do?
Be in the middle, kind of like the middle value.
Well, the middle, well actually the middle value would be the median as well, wouldn't it? Right? How do you actually find the mean of some data?
You add up all your data and divide it by how much.
Add up. So if you had to explain the mean to some primary school kids that have never done it before, and you had a big bag of jelly babies, how would you go about using that big bag of jelly babies with a group of 10 little kids to explain the mean? What could you do? Yeah?
Okay. You could like split up all the colors and say like, okay, like we have like 2 blues and like 3 reds and like 5 oranges. So what's like the average amount that in each color?
But if you've split them up into oranges, how can I have a mean number of oranges when there's only one number of oranges?
No, like you do like the mean number of jelly beans in each color. You know?
That makes sense.
Does it?
Yeah.
But if I've got 5 blues, 3 reds, 15 oranges, what's the mean number of oranges?
23 divided by 3.
That's not the mean number of oranges.
No, but like the mean in each group
Oh, okay.
of colors.
So a mean number of sweets. So are you overcomplicating it by splitting into colour then?
Yes.
Could we not just give out the sweets to kids in different numbers?
Yeah.
So have a handful, isn't you have, so I'm going to give Izzy a big handful, and I'm going to go over here and give Sophie just a couple, right? I'm going to spread out my sweets, so everyone's got a different amount of sweets, yeah? Got that?
Yes.
I could even say to kids, right, next lesson you turn up with some jelly babies, all right? I'm not going to tell you how many to bring in, but you bring in some jelly babies. So somebody would go, oh, my mum only let me bring in 2, all right? Someone would go, all right, my parents had a big bag, I brought in 48, all right? So they've all got different amounts of jelly babies. What would you then tell them to do to find the mean number of jelly babies, and then the purpose of having a mean? Well, I would do this. This is how I would explain. I go, right, I'm going to take everyone's jelly babies, and I'm going to put them in one big pot. All of you, all in one pot. What's that the equivalent of doing numerically?
Adding them up.
Adding them all up. Right? I am then going to share them out equally amongst you out. And that's dividing by the number of people. Yeah? Now all of you get the same amount, yeah? And that would actually be the mean amount of sweets. And you all get the mean amount. Assuming I can do that. Just say, theoretically, you've all got exactly the same number of sweets. And that mean number of sweets is what you'd end up with. Now, what would some of the children say? Are they happy or are they upset?
Some of them who brought in like 50 would be upset if they got like 20, and then the people who brought like 3.
Yeah. So the 2 extremes, can you see how the mean now affects things quite big? So if I've got a student who brought in 50 jelly babies, and one student that brought in 1 jelly baby, and actually they end up with 10 each. Right? The one that had 1 jelly baby is great. I get 10 jelly babies and I brought one. The one that had 50, what are they looking at? They're looking at, well, I brought in 50, I've only got 10, and all the rest have been shared out amongst everyone. Why should they get them? Well, that's what the mean is like, yeah? Right. What would be the nicest thing to happen if I did that thing with a group? How would it be that if no one was upset?
They all got the same one.
Well, they're all going to end up with the same.
If they
How
all,
could I ensure that? Well, I can't ensure it, but what would be the situation that would happen if they're all happy at the end, happy-ish?
they all brought like the same amount.
Yeah.
almost.
Like a similar amount.
Yeah, exactly. They're not going to bring exactly the same,
Yeah.
but let's say they all brought one packet that they bought from the same shop, and so some had 8, some had 9, some had 10. Yeah? But they all have a balance. So if I had 8 and I can see I end up with 9, yeah, all right, I get one more. It's not a big deal, is it? If I had 11 and I end up with 9, it's not a big deal, right? Does that make sense? So if all the amounts were roughly the same, that mean would keep everyone happier. And is that mean quite a good representation of the whole data set? Yeah? But what if I have data that is, I've got 5 students that brought in 50 or 60, and I've got 5 students that brought in 1, yeah? And then everyone in the middle either brought in 3 or 4, or some brought in 28, or what if I've got a real spread of data? The mean could still be 10. Does that make sense? So if I plonk them all in a pot, the ones that brought in loads are balanced out by the ones that didn't bring in any. Yeah? Got that? The pot still ends up with the same amount. When I dish them out, the mean is still the same. Everyone ends up with 10. The ones that brought in loads, unhappy. The one that brought in not many, unhappy. Alright? Make sense? So that's how you can have different distribution of data. Now, what would you say about the reliability of the mean when the data is really spread out like that? Well, think about how unhappy some of the students would be.
Not reliable.
Not reliable. So if we think about that, some students are really unhappy, some are really happy, but that's not what we really want. We think in terms of happiness. We want a situation where everyone's just, yeah, fine, I got what I came with, roughly. A little bit better off, not so much, whatever. But I don't want some people really unhappy and some really ecstatic, because that shows a difference. The mean is not great. So really, I want a mathematical way of deciding, well, how useful is the mean? How good is it? Right? So we're looking at determining how spread out the data is compared to the mean that I'm using. Right? So that is how reliable. And we are going to use this new number that we're going to calculate as a verification that the mean is a suitable measure of central tendency. So all these words I'm giving you now, it's sounding more complex. Can you hear that in the vocabulary I'm using? That's because it's an extended topic. Right? So you need to get used to that. So we're talking about, is the mean reliable? Does it represent the data well? I'm going to verify that the mean is a reliable source of a measure of central tendency. And I'm going to do that by calculating what's called, you may have already come across it in science, I guess. I don't know why my computer is going slow. Standard
Deviation.
deviation.
I haven't heard of it, but I just.
It's called standard deviation. Because the video is running, my pen's getting slow, which is really annoying. So, what we're going to do is we're going to calculate the standard deviation. And you can do standard deviation of the population, which is what we're going to do. But you can also do the standard deviation of the sample. And you know what we mean by a sample. And there is a symbol. standard deviation of the population has this symbol. And the sample tends to have this SX. Okay. Now, I'm just going to say this quick, I'm going to pause and I'm going to let you have a little chat. If you had to come up with something called the standard deviation yourself, what the standard deviation does is it looks at the mean and then looks at the data that the mean comes from and compares them. Yeah? Got that? If you had to compare the mean to the actual data, so bear in mind, like I just said about jelly beans, there could be two completely different sets of data, but the mean could be exactly the same. Got that? So one mean is useful, good. We've got lots of perfectly normal kids with their jelly beans munching away. And then I've got one class with some really ecstatic kids with loads of sweets, and more than they had, and some really unhappy. There's about to be a fight happening. Right? Their mean is not useful. What would you do to compare the mean with the data that comes from? What would you do? Just a couple of minutes, have a chat to the person next to you. What would you come up with? And then we'll talk about what's actually done and see how close you were. So, standard deviation, before I give you the formula for working it out, is, come on computer. The standard deviation is the mean, say, the mean distance of each point from the mean.
Not that bad.
No, I get it. Does that make sense? The mean distance of each point from the mean.
We have to do that?
Yes.
Like physically, like ourselves.
Physically yourself. Yeah. Actually, when you get to, well, if we had GDCs, your graphic calculators, it does it for you.
Are we like
Excel
allowed to
does it
have
for
those
you.
now?
It'd be great if you all had the GDC, the TI-84s or Inspires. It'd be brilliant. We could really get, you can't use them in your e-assessment, but when you get to diploma, if you already know how to use them, awesome. Brilliant. They are quite expensive, but you can't do diploma without them. 200 something.
For a calculator.
Oh my God, that's like, it's like a quarter of the price of my phone.
It's called every day. Yeah,
It's a calculator, yeah. Well,
calculator can't call him.
feel free not to do diploma. They play games, you can program it, play games. The mean, and it does standard deviation for you, so you don't have to do it all by hand. So it does say the mean distance of each point from the mean. So basically, standard deviation looks at, kind of like Daphne was saying, you don't just go the extremes, all right? You go for every single point and you work out how far away it is from the mean. Right? You work out, you subtract them all, every single point. You subtract it from the mean and work out that, and you add all those differences up and divide by the number of differences you have. And that will tell you the mean difference. So therefore, the larger the mean difference, what can you say about the data?
The less reliable.
Because it's more spread out, dispersed, yeah. It's more spread out. So if the standard deviation is larger, it means the mean is not a very good representation of the data. Does that make sense? Okay, so I'm going to give you a formula now. I'm going to do it step by step. Right, so we're looking at the mean distance of each point from the mean. So what I'm going to do is this. X bar. Remember what that means?
We learned.
What?
Did we learn it?
Yeah.
I haven't mentioned it. It's what? Not a sample. Remember we did it with the scatter plots. Yeah, I know. You're the only one that's bothered to read the book.
Is the mean of all the x values.
This is the mean of the x values, yeah? So bear in mind we have no y values. This is the x mean. This is the mean value of all my points. So what did Daphne start us off by saying? We need to subtract all the points. Alright? So x is the mean of the values, and well, x bar is the mean, x is just each point. Alright? But this is only doing it once, so we might have to introduce you to a bit more data. Now the next thing you might go, ooh, why are we doing that?
So what's the x is just
Any point.
Any point, any individual number. And you'll get, well, how can we then do it to every single point? Well, I'll explain in a sec. So I've got the mean, subtract, this can go either way round. So if it says something different in your formula book or in your book, then it's fine, because of what I'm about to do. And we have discussed why this is a good idea. I'm going to square that number. Why am I going to square it?
Get rid of the x.
Doesn't get rid of the x.
2.
What does squaring a number do, though? It does get rid of something. But what does it get rid of? Let me just
Square
ask you
root.
something. You've got a mean. If
Get
I
rid of
subtract a
square
number,
roots.
what are the possible answers?
Anything.
Anything. So the mean is 3. Could I have a number that's 5?
Yes.
oh it makes it
Positive, yeah? Some of the numbers will be above the mean and some will be below. And if I just work out the difference and always make... Remember, it's a computer doing it, not you. Remember I said, you know if it's a difference to always write a positive answer, yeah? What's the difference between 3 and 5?
2.
What's the difference between 3 and 1?
2.
The computer doesn't know that. It would say 2 and negative 2. If you add 2 and 2 together and divide by 2, what do you get? Right. If you add 2 and negative 2 together and divide by 2, what do you get?
0.
0. So if you've got some points above and some points below, like the kids with lots of sweets and the ones with none, if you work out the difference, they're going to balance each other out potentially, aren't they? Right, they're going to become a difference of 0. And we don't want that. So we've got to get rid of the negatives. And the only way to do that is to square it. But what do we have to make sure we probably have to do at the end?
Square root.
Square root. So we're going to have to square root. But we've got our things, we've got our differences, we've squared them to get rid of any negative. Right? But what do we need to do then? We're finding the mean distance of each point from the mean. So this is the distance of each point from the mean. So how do I find the mean distance? Well, first of all, we have to add them all up. So this might be new to you. We've got this symbol. This symbol here, if anyone uses Excel, is called a sigma. And in Excel, it's called auto sum. And it means to sum of, add them all up. That's what sigma means. And it's in Excel on your computer. If you click on auto sum, it'll have that little sigma button. So that means add up all the differences that are currently squared. Then we need to divide by, not x, because x means one of the numbers. We actually need to know, divide by the total frequency. Now this might change depending on whether you've got groups data or not. And it's alright, you have another version, it's good to build up. Okay? So that is, find the distance, square it to get rid of the negatives, add all those up, divide by the number of numbers I've got, which is the mean, but what did we say we needed to do at the end? Square root. And that is our standard deviation. It's not a very good word. Standard deviation. So that's how we do our standard deviation.
Wait, what does the F mean again?
Frequency.
Wait, so standard deviation is that like lopsided 6 with the X? So what was the S with
What?
the X? You know what I mean?
Population and sample.
Oh,
So if you turn to page 82, I think it's 82, actually 79, let's do 79. Alright.
And the extended or the normal?
Is that it?
Oh, sorry.
Page 79, right, in the extended book. You will actually see a slightly different version of that formula. Alright? Have a look in the pink box at the bottom of that page. It is slightly different. So I've written it in a way using symbols that you maybe have seen before. But on that page, because you've got this in a formula booklet, it says that the standard deviation is still the sum of, but in this case they've done this the other way around, so they've got x minus and they've got this symbol. You should recognise that as well. So x bar is the mean of x, but this is
Mean of the population.
the mean of the population. Yeah?
It says it's in
Yeah. It's in the book. Alright? That's the mean, it's just the mean, rather than have it as an X or a Y. And do you know how to pronounce that letter?
U.
M.
M-U, mu.
when you said M and she said U and two letters up. Mew.
It's a mu,
That's what I'm gonna name my dog.
You.
right? And it's used to represent the mean a lot. Now you'll also see there's a couple of ways to write. We could put n, but there's also this sum of the frequencies. Why is it the sum of the frequencies? I know it says n there, but if you turn to page 82, you'll see another slightly different version.
Oh my god.
Because what type of data? So they also, with this one, they include an F in there too. F times that. What is that for? What's F stand for again?
Frequency.
F frequency. Because what type of data could we have to deal with?
Group.
Group data, yeah? Where we've got 10 of these, and we've got 11 of those, and we've got 23 of those. So if I've got 15 12s, I can do 12 minus whatever the mean is, and then multiply it by how many times it happens. So it's just generalizing it in a formula, but it doesn't mean anything different as such. You'd probably end up doing it yourself anyway. Yes?
In the book, it doesn't have the like X after the 6. Are we supposed to put that?
What's 6?
The thing that looks like a sideways 6. No.
Well, I said this was the one we came up with to talk about, but this is
Yeah.
what's in the book. If you look at page 79 and 82.
Yeah, but like doesn't have the like X after
Right
the.
here.
Oh,
After
okay, okay.
But can we put it anyways?
Well, why actually? Sorry, I shouldn't have written it. Why should there be no X there?
Oh.
Because this is not an X, but it's fine because I've used an X in here. It just means the standard deviation of the X values. It's not a big.
So we write
Yeah.
both of those.
As long as you understand what it means, and it means no real difference. So this is what we came up with. This is what you might see in a formula booklet. It's just dealing with F or N for the number of terms. It's whatever. As long as you understand what that means. Okay? So we should just summarize and say a larger standard deviation means a larger spread from the mean. Okay, so a larger standard deviation means the data is spread out more from the mean. If the standard deviation is 0, what does that mean about all the points?
They're the same.
And they're all the same as?
The mean.
The mean, yes. So as the standard deviation gets bigger, that means the data is spreading away from the mean. Could be above or below, we don't know, because it doesn't matter. The squaring gets rid of it. All right, so next lesson we'll have a look at how we can actually do these calculations and how we can